This lesson corresponds to section 14.2 in Math in Our World. This section is on Euler paths and Euler circuits. An Euler path is a path that travels through every edge of a graph once and only once. Each edge must be traveled and no edge can be retraced. So as you can see here, the Euler path starts here at point A. Then it goes to B, from A to B. That's 1. And then 2 is from B to E. That's where it goes next. So this is a good way to number your edges when you do your Euler path. And we have to go through each edge once, one and only one time. You can't retrace an edge or go over an edge again. So and this has to be done by trial and error. You try this, you try that, and if it doesn't work, you try something else until you come up with a path that will take you through each and every edge and will not retrace any edge. So that's what we call an Euler path. And an Euler path does not have to end up where it starts. But if it's an Euler circuit, it has to end up where it started. So the Euler path, we're starting at point A. We're going from A to B. Then we're going from B to E. So we're getting this edge. There's 2 edges we've gotten. 1, 2. Okay, then we're going from E to F. So this is number 3, the 3rd edge. And then we haven't gone over any, so we're good so far. We haven't retraced any edges. And then we're going to, for our 4th edge, we're going from F to D. And then for our 5th edge, we're going from D to B. So far we haven't traced any edges that we've already gone over. And then for 6, we're going from B to C. It's okay to go through a previous vertex, but you can't go through a previous edge. So we go from B to C, that's number 6. And then we go from C to E, that's number 7. And then we go from E to D, that's number 8. And then we go from D to G. And that's the end of this Euler path. If you look back, you'll see that we have gone through each one of the edges, and we have not retraced any of the edges. And notice that when you have a path, you don't have to end up where you started. I started at point A, but I ended up at point G. So that would be the Euler path. And you can use letters to indicate this path. You would have A, comma B, comma E, comma F, comma D, comma B, comma C, comma E, comma D, and then comma G. That would be the path. You can put a comma between each one, or if you have an arrow going to the right, that's used sometimes between each vertex to show symbolically, by using the letters, to show the path using the letters. Now, next, we want to talk about an Euler circuit. Now, the Euler circuit is very similar to the Euler path. The only difference is that when you have the Euler circuit, you have to end up where you started. That's the only difference. You have to go through each edge once. You have to go through each edge once, and you have to end up where you started. An Euler circuit is a circuit that travels through every edge of a graph once and only once. Like all circuits, an Euler circuit must begin and end in the same vertex. So, inner circuit, Euler circuit starts and ends here. So it starts at point A and it ends at point A. And you don't just get these Euler circuits usually just like that. You have to try this, try that, and after you try several things, finally you figure out what works. That's how the Euler circuits work. So be sure to be aware of that. But as you can see here, after several tries, we have figured out here that first you go from A to B. That's number one. And this is a good way to label your edges when you're doing your Euler diagram. When you go from one thing to another, make that number one. Then when you go from there to the next thing, make that number two. Then the next one, number three, number four, and so forth. So we're going from A to B. Then we're going from B to E. That's number two. Number three is from E to F. That's number three. Number four, we go from F to D. So we haven't retraced any of the edges yet. Then we go, number five, we go from D to B. We haven't retraced anything. It's okay to go through a previous vertex when you're doing an Euler circuit. Then we go from B to C, that's number 6. Then we go from C to E, that's number 7. Then we go from E to D, that's number 8. Then we go from D to G, that's number 9. Then we go from G to A, and that's number 10. We end up where we started. And once again, this is an Euler circuit. For the Euler circuit, you go through each edge once. Additionally, you have to end up where you start. The following statement, this is Euler's theorem. The following statements are true for connected graphs. So these are connected graphs. You don't have like two separate parts of one graph when they're connected. When they're connected, there's a path that you can go from any vertex to another vertex, any other vertex. So that's what we're talking about here for a connected graph. If a graph has exactly 2 odd vertices, then it has at least one Euler path, but no Euler circuit. Each Euler path must start at one of the odd vertices and end at the other one. If a graph has no odd vertices, all even vertices, it has at least one Euler circuit, which by definition is also an Euler path. An Euler circuit can start and end at any vertex. If a graph has more than 2 odd vertices, then it has no Euler paths and no Euler circuits. Once again, if a graph has more than 2 odd vertices, then it has no Euler paths and no Euler circuits. So these rules can be used to decide whether or not you have Euler paths and Euler circuits. So you have to refer to these rules. When we have a test or a quiz on this, you don't have to memorize these rules. When we have a test or a quiz, you will be allowed to use these rules if you have these rules on the test or the quiz. Example 1, using Euler's theorem. Explain why the graph in the figure has at least one Euler path. Use trial and error, and this should be part B. Use trial and error to find one such path. So we're going to explain why the graph in the figure has at least one Euler path. And we can do this by using Euler's theorem. As indicated here, we count the number of edges at each vertex to determine if the vertex is odd or even. So we look at vertex A. There are two edges intersecting A, so A is even. We look at B. We have 1, 2, 3, 4 edges intersecting vertex B, so B is even. We look at C. We have 1, 2, 3, 4 edges intersecting C. C is even. We look at D. We have 1, 2, 3 edges intersecting D, so that means that D is odd. And we look at E. We have 1, 2, 3 edges intersecting E, so that means E is odd. So you can see that on this graph here. As we said, A is even. We have 2 intersections there. B is even, C is even, D is odd, and E is odd. So that's what we have. And then, of course, we go back and read Euler's theorem, and we make our decision. We see from the figure on the left that there are exactly 2 odd vertices, D and E. And if we just go back to the previous, if a graph has exactly 2 odd vertices, then it has at least one Euler path. So that's the reason that this graph has at least one Euler path. The reason is because the graph has exactly 2 odd vertices. And those 2 odd vertices are D and E. As indicated here, we see from the figure on the left that there are exactly 2 odd vertices, D and E. Thus, by the first statement in Euler's theorem, the graph has at least one Euler path, but no Euler circuit. Part B, Euler's theorem says that a possible Euler path must start at one of the odd vertices and end at the other. To do this, we use trial and error. So we're going to start at D and we're going to end at E. So we keep trying different ways and going different ways until we figure out what works. So that's what we've done here. We figured out that first you go, see the 1, that's number 1. That means first we go from D to C. That's number 1. Number 2, after that, we go from C to B. We haven't retraced any edges. Then after that, number 3, we go from B to E. We still haven't retraced any edges. And then after that, you see the 4 here, that means we go from E to C. 5 means we go from C to A. 6 means we go from A to B. 7 means we go from B to D, 8 means that we go from D to E. So we have gone over every edge and we have not retraced any edge. So this would be an Euler path. We didn't end up where we started. We started at D, we ended up at E. So we know this is not an Euler circuit, because for Euler circuit, you end up where you started. We can use Euler's theorem to solve problems involving situations modeled by graphs. So we had this situation here. You have the right bank, you have islands, island A, island B. You have the bridges connecting the islands and so forth. And you can do a graph of this. And this is what the graph would look like if you graph this situation that we have here. You have A, L, B, R. Those are your points. Those are your vertices. And so you look at this point. You have 1, 2, 3. You have 3 edges that are intersecting this point. So this point here would be odd. You look at this point, you have 1, 2, 3, 4, 5. 5 edges that are intersecting this point. So this point would be odd. Look at this point, you have 1, 2, 3. 3 edges intersecting this point or this vertex. So this one would be odd. Look at this one, you have 1, 2, 3 intersecting that one. So all of these are odd. All of these are odd. Count the number of odd vertices. So we have 1, 2, 3, 4 odd vertices. There are 4 odd vertices. Because the graph has more than 2 odd vertices, it has no Euler path. And this is stated in Euler's theorem. Thus, there is no possible way anyone in Königsberg can walk across all of the bridges without having to recross some of them. That's what that means in Laban terms. Okay, let's talk about Fleury's algorithm. Fleury's algorithm can help us find Euler paths and Euler circuits. This discussion is on finding possible Euler paths and Euler circuits by using Fleury's algorithm. If Euler's theorem indicates the existence of an Euler path or Euler circuit, one can be found using this procedure. So Euler theorem would tell us whether or not we have Euler paths and Euler circuits. And then we can use Fleury's algorithm to help us find them. Instead of just using trial and error, we can use Fleury's algorithm. Number 1, the first step of Fleury's algorithm: if the graph has exactly 2 odd vertices, choose one of the 2 odd vertices as the starting point. If the graph has no odd vertices, choose any vertex as the starting point. Number the edges as you trace through the graph according to the following rules. After you have traveled over an edge, erase it. Show the edge as a dashed line. So this is a way to help you to keep track of things. You can also keep track of things by numbering the different edges that you go over. When faced with a choice, and this is important, of edges to trace, first choose any edge that is not a bridge. And we said a bridge is an edge that if you take it out, you have a disconnected graph. So once again, when faced with a choice of edges to trace, first choose any edge that is not a bridge. So you save your bridges until last. A bridge is an edge whose removal would make the graph disconnected. Travel over a bridge only if there is no alternative. So any bridge that you see, save it until the end. Using Fleury's algorithm, the figure has at least one Euler circuit. Find one by Fleury's method. Notice the figure has at least one Euler circuit because the graph has no odd vertices. That's the second statement of Euler's theorem. So as you can see, we have vertices A, B, C, D, E, F. And then we have the different edges that are joining the various vertices. The graph has no odd vertices. This is the solution. So we can begin at any vertex. We choose vertex A as the starting point and proceed as follows. And as you can see here, travel from A to D and erase edge AD. We can also travel from A to C. That's step one. Step two, travel from, so once again we went from A to D. That's number one. So we made it a dashed line. Then step two, travel from D to C and erase edge DC. So we erase edge DC, we put a dashed line there. That way we can keep track of everything and make sure that we don't go over anything, any edge twice. CA is a bridge. CA is a bridge. So we leave that. We don't do that now. It is where removal vertex A would be isolated from the rest of the graph. If we remove that, vertex A would be isolated from the rest of the graph. So it would be considered a bridge. So we save that for last. Step three, travel from C to F and erase edge CF. So we're traveling from C to F. We erase CF. That was step three. Step four, travel from F to D and erase FD. So we're traveling from F to D. We erase FD for the dashed line. Travel from D to B and erase edge DB. So we erase that edge, we put a dashed line. Travel from B to F, right around here, sort of like a circular fashion there. Travel from B to F. F to E, okay, that's across here, F to E. E to C, okay, coming back here, E to C, and finally C to A, and erase the respective edges. And there we have it. Thus, the Euler circuit is as indicated here. This shows the Euler circuit using numbers. Okay, first we go here, second we go there, third we go there, fourth we go there, fifth we go there, sixth we go there, seventh we go there, eighth we go there, ninth we go there. And it is a circuit, as you can see. We ended up where we started. We started at point A and we ended up at point A. And we went through each edge once. Now you can use letters to represent this. If you have a right arrow on your computer, you can put an image of that on the screen. You can say A arrow, D arrow, C arrow, F arrow, D, and so forth. If you don't have an arrow, then you can use a comma to show the path that you use, to show the circuit that you use. You can put A, comma, D, comma, C, comma, F, comma, D, comma, B, comma, F, comma, E, comma, C, comma, A. You can write that down, write those letters, and that can represent your path. So you could put the path on the graph. That's great, but you also should be able to write the letters to represent the path or the circuit that you take. And that's it as far as Euler paths and Euler circuits are concerned. And Fleury's rules for finding Euler paths and Euler circuits. So I hope this will be helpful in doing your homework. Your homework for this section, which is section 14.2 in your textbook. If you're using a different textbook, your professor will give you appropriate assignment. If you're just doing this for enrichment, then you can find the textbook or find some problems online, or find the textbook in the library that will have some problems in it. But for Math in Our World, section 14.2, at the end of that section, at the end of section 14.2, you want to do problems 1 through 6 all, 7 through 13 odd, and 21, 27, and 31. And these problems deal with Euler and Fleury. Have a great day. Bye now.